You're here because you want to master carboxylic acid and its derivatives with a University of Cambridge graduate. Let's begin. In this video, I'll be doing a quick summary on the reactions that your carboxylic acid and its derivatives can go through, as well as some of the reasoning behind some of the reactions as well, like why carboxylic acids are so acidic. So your carboxylic acids are mainly defined by the C double bond O with an OH group right over here. And you should be very familiar with some of the carboxylic acids by now, such as ethanoic acid. And its derivatives comprise of esters and acyl chlorides, which I'll run through later as well. Now, how we prepare carboxylic acids is actually pretty straightforward, and this is because I've already run through most of them in my previous master classes already. For example, I can oxidize my primary alcohols or my aldehydes to carboxylic acids, so you can refer to my hydroxy compounds masterclass in order to get the reagents and conditions as well. You can also do oxidative cleavage of alkenes to give your carboxylic acids, and you can refer to my alkenes masterclass for that. You can also do side chain oxidation of arenes to give your carboxylic acids, or more specifically your benzoic acids, so you can refer to my arenes masterclass. And you can also hydrolyze your CN group, or your nitriles basically, to carboxylic acids, and there you can refer to my halogen derivatives masterclass. As you can see, we've already covered carboxylic acids a lot in our previous master classes already, so I won't be repeating them here. So if you haven't already memorized or you've already forgotten some of the reagents and conditions from these master classes, do refer to my previous videos to check them out and do a quick revision of them. Next up, what are some of the reactions of carboxylic acids? Well, we've already run through esterification in my hydroxy compounds master classes, where you can react carboxylic acids with alcohol in order to get your esters. You can also prepare your acyl chlorides. Now this is new, so I'll be running through it. Your carboxylic acids can react with PCl3 in heat to give your acyl chloride, or you can react with PCl5 to give your acyl chloride, and it can also react with your thionyl chloride, which is SOCl2, under heat to give your acyl chloride. So this is very similar to the reactions that we've run through in the hydroxy compounds masterclass as well, except that your carboxylic acids can run through the same reactions as well. Now, do take note that the observations of white fumes of HCl are present for your PCl5 and your SOCl2. You might also want to memorize the byproducts of this reaction as well, so that you can have an easier time when it comes to balancing the equation during the exam. Now, as for acidity, of course carboxylic acids are acidic. In fact, they are stronger acids than phenols and your alcohols. But why? This is because this salt over here that you produce after dissociating out the H+, RCO2-, it actually forms resonance structures, shown over here. And this will help to delocalize the negative charge over two highly electronegative O atoms. You will stabilize the negative charge greatly. And because of that, it's very energetically favorable to form these resonance structures. Therefore, it's also very energetically favorable for your H+ to dissociate out. So that's why carboxylic acid is a pretty strong acid. Now do refer to my hydroxy compounds masterclass as well when it comes to comparing the acidity between carboxylic acids and your alcohols and your phenols and water. And make sure to use the explanations found in those masterclasses there as well when you're comparing. Now do take note that also the number, proximity, and strength of your electron withdrawing / electron donating groups to the C double bond O or the CO2- group is important when considering the acidity of your organic compound, because all these factors do affect your negative charge on the anion, whether it stabilizes or it destabilizes the negative charge, and hence it affects how strong an acid or how weak an acid is for this organic compound. You can also reduce your carboxylic acids to alcohols, again already covered in my hydroxy compounds masterclass. And you can also have a very good distinguishing test for carboxylic acids, because carboxylic acids are strong enough acids, it can react with sodium carbonate, and hence you can get this effervescence of CO2 that forms a white PPT in lime water. Next up, we're going to cover one of the carboxylic acid derivatives, acyl chlorides. So your acyl chlorides can undergo hydrolysis to form your carboxylic acid as well with this reaction. Now, quick comparison as to which is easiest to hydrolyze, whether it's acyl chloride or an alkyl chloride or an aryl chloride, which is a benzene ring, which is this. Okay. We can look at several factors. So the easiest to hydrolyze is acyl chlorides. It's because of a very high delta plus on the carbon, because it's bonded to a very strongly electronegative oxygen and chlorine. That's two atoms that give it the delta plus, and therefore it attracts a nucleophile very strongly. Also, there's very little steric hindrance because it's a trigonoplanar carbon. Now, when you react it with silver nitrate, the observation is that a white PPT of AgCl would form immediately. Now, if you look at your alkyl chloride, it's harder to hydrolyze than your acyl chloride because, one, it's only bonded to one electronegative Cl, so it has a lower delta plus, and the CCl bond can only cleave with heating. Furthermore, there's also more steric hindrance for the nucleophile if it ever approaches the carbon. This is because the carbon is in a tetrahedral shape and not trigonoplanar. And evidence is when you react with silver nitrate, this white PPT of AgCl only after very prolonged boiling. But do take note that if you use ethanolic AgNO3, it's faster, meaning it will faster form the white PPT. Now onto your aryl chloride. So this is the hardest to hydrolyze. And this is because the lone pair in your chlorine is going to delocalize into the benzene ring. There's overlapping of this p orbital for this lone pair. And because of this, you will attract a nucleophile less strongly as well. And your CCl bond will have a partial double bond character as well. Kind of similar to how your phenols can also not undergo nucleophilic substitution as well. And thus, there wouldn't be a cleavage because the CCl bond is like a 1.5 bond. It's pretty strong. Your electron-rich benzene is also going to repel the nucleophile, and there's also steric hindrance from the benzene ring. And the evidence is when you react with silver nitrate, there's really no PPT even after prolonged boiling, or if you use ethanolic AgNO3 as well. Your acyl chlorides can also undergo esterification when it reacts with alcohols. So do refer to my hydroxy compounds masterclass on that as well for a quick refresher. Next up, we're going to talk about esters. So how we prepare esters, I've been running through it time and again in this video as well. It can be prepared from your carboxylic acids or your acyl chlorides reacting with alcohols. So do refer to my hydroxy compounds masterclass for that. You can also react esters away. So they can undergo hydrolysis, so either acidic hydrolysis or basic hydrolysis to get your carboxylic acid or carboxylate salt, and you can also reduce your esters to alcohols as well under lithium aluminum hydride in dry ether. So that's all for carboxylic acids and its derivatives. Again, I must emphasize that most of this knowledge over here is already found in your previous chapters or in my previous masterclasses. If you like this content, be sure to hit the subscribe button so that you can get more frequent updates from this channel. If you want to enroll in my online class, be sure to also hit the link below so that you can book a free call with me and I can run through your past papers and go through any doubts and clarifications for chemistry that you might have and show you why my class is the best fit for you. I'll see you in the next video.